Okay, now in lecture 13, we're going to take a look at implementing binary search trees, which are just a little bit more complicated than singly linked lists. Again, we're going to have a collection of dynamically allocated nodes connected to one another with pointers. We've already discussed binary search trees using Python, so we don't really need to rehash the theory and the lookup time performance being log n and so forth. Here on slide 3 is a diagram of a small binary search tree. We have 12 in the node at the top. All the values to the left are less than 12. All the values to the right are greater than 12. And here is the beginning of a code file implementing the data structure and a collection of interface functions for managing a binary tree. We're going to call each node in the binary tree a BT node structure. Each node in the binary tree contains a certain value, which is the data in that node. And each node has a left child and a right child. Left and right are each pointers to other BT node structures. Our function for creating an empty binary tree, mic empty binary tree, simply returns null pointer. So that's pretty straightforward. We could create more make binary tree functions that, for example, built a binary search tree from an array of integers or what have you. Here we have a function called putBinaryTree, whose job is to display the values in the binary tree in ascending order. It is a recursive function. It does not change anything about the binary tree. So the pointer that we pass in is a pointer to a BT node that's treated as const within this function. If the tree is initially empty, that is, if this top pointer is 0, nothing happens. But if top is not 0, that implies that there are things in the tree. So we're first going to display the left-hand side of the tree. Then we're going to display the current value followed by a space, followed by the right-hand side of the tree. So if my tree actually looked like what we have on slide 3, and I called putBinaryTree with this top pointer passed in as the top parameter, what I'd get out would be -4, 7, 9, 12, 13, 29. That is the 6 items in this binary tree in ascending order. Here on slide 6 is a brief outline of a main function exercising our binary tree. We have top as the header node, keeping track of where the binary tree starts. We're using mic empty binary tree to set up top to point to an empty tree. It may seem silly to call a function rather than just saying top gets null pointer, but we might in the future change how our header node is implemented so that setting top equal to null pointer in main might not be the appropriate thing to do. Having created this empty binary tree, we're then going to call a function named binaryTreeInsert several times for 12, 7, -4, 13, 9, and 29. And because this function is changing the shape of the tree, we're passing in the address of the header node rather than a copy of the header node. PutBinaryTree, of course, is not changing anything about the tree, so we're just passing in a copy of the header node. And in fact, in the putBinaryTree function, we're treating that as a pointer to a BT node const and promising not to change the tree at all. Then finally, when we're done using our tree, we want to delete the tree in the same way that we deleted our linked list so that we don't have any memory leaks if we expand this main function to do more things. And because, of course, deleting the tree is going to entail changing the top header node to null when we're done, we're going to pass in the address of top to that binary tree delete function. All right, now let's take a look at the implementation of this binary tree insert function on slide 7. Here we are. Since the first argument is the address of top, and top is our header node, top is a pointer to a BT node, the parameter that receives that value, which we're calling ptop, has to be declared as a pointer to BT node. The second argument being passed in is simply the integer value that we want to store into our tree. So let's see what happens when we call binary tree insert, passing the address of top and 12, with the tree being initially empty. Okay, so the tree is initially empty, meaning in the stack we have a stack frame for main, and its top header node variable contains 0. Nothing is in the heap yet. When we call binary tree insert, the first argument that we pass in is the address of top, which gets stored into this ptop parameter, and the value 12, which is the value that we want to insert. So a stack frame for binary tree insert is going to get created, and I didn't want to spell out binary tree insert, so I abbreviated that as BT insert. But here we have the stack frame for BT insert. ptop is pointing at main's variable called top, and val contains 12. Okay, now if the tree contains values already, that is, if star ptop is not 0, then we're going to have to traverse our way to the bottom of the tree in the appropriate place to add this value 12. But in our case, star ptop for this empty tree is 0, so we're going to drop down to this else part and say star ptop, that is main's top pointer, gets the address of a new BT node with value 12 and null pointers for the left and right subtrees. So here's that happening. We get a newly allocated BT node. The value gets filled in with 12, and the left and right subtree pointers are filled in with nulls, zeros. New returns to me the address of this newly allocated node, and I'm assigning that address into star ptop, which is top back in main. Okay, so binary tree insert returns now, and we are in this situation. Back in main, our top variable is now pointing to the topmost node of a tree that is only one node in size. Let's suppose that we call binary tree insert again, passing in a value of 7. Here's a more fleshed out version of the main function showing that we're inserting 12, then inserting 7, then -4 and 13. I'm not going to do all of these. I'm just going to do 12 and 7 to give you the idea. But let's see what happens when the address of top gets passed in along with a value 7 to binary tree insert. Okay, so once again, we're going to get a stack frame for binary tree insert. ptop will be pointing at main's header node, main's top variable, just like before. The difference is that now the val parameter in binary tree insert is 7 rather than 12. We start executing the code if star ptop. Well, we're asking, is there already something in the tree? Okay, here's ptop, here's star ptop, and star ptop is non-zero, so we have to figure out now how to find the bottom of the tree to put our 7 in the correct place. We ask, is the value we're trying to insert, which is 7, less than, all right, here's ptop, star ptop is main's top variable, and star ptop in parentheses arrow value is 12. So we're asking, is 7 less than 12? It is, so that means that we want to insert the 7 to the left of the 12. Therefore, we call binary tree insert with the address of the left subtree in star ptop. All right, so here's ptop, here's star ptop. Star ptop in parentheses arrow left is this pointer, the left data member of this BT node, and we are passing the address of that thing down to another invocation or another call of binary tree insert. So here's what happens now. We call BT insert recursively, and the ptop parameter in this recursive call is pointing at the left data member of the node that contains 12. The value that comes into this recursive call of binary tree insert is just 7 again. Now we start executing the code for binary tree insert, and we say if star ptop. Well, ptop now is pointing at the top of the left subtree, and the left subtree is empty. That is, star ptop in the recursive call to BT insert is 0. So once again, we drop down to the else, and we say star ptop gets a newly allocated BT node with 7 and null pointers for the left and right data members, the left and right subtrees. So here is that happening. We've allocated a new BT node. 7 got filled in as the value. 0's got filled in for the left and right data members, the left and right subtrees. And the address that new returns to me gets stored in star ptop, which is the left component of the node containing 12. So we have successfully put the 7 to the left of the 12. The recursive call of BT insert now returns, and the outer binary tree insert, the first level binary tree insert call, also returns. And so we find ourselves back in main with top pointing at the node containing 12, which in turn on the left side points at the node containing 7. And as we continue this, the -4 will go to the left of the 7, the 13 will go to the right of the 12, the 9 will go to the right of the 7, and the 29 will end up going to the right of the 13. And so that will get us eventually to the diagram that we started out with here. Okay, so returning to our main function on slide 8, we have inserted, well, we have first created an empty binary tree. We have inserted 6 values into the tree. Then we're going to call put binary tree, which will display those 6 values in ascending order. The second part of the main function we have modified a little bit to call a couple of other interface functions. Binary tree is empty is an example of what's called a predicate function. It returns either true or false about some characteristic of the data structure. So in this case, if the binary tree is empty, the binary tree is empty function will return true. Otherwise, it will return false. If binary tree is empty returns false, then in this else part, we're going to call binary tree min, which will return the minimum value contained within the binary tree. The implementations of these two functions, binary tree is empty and binary tree min, come a few slides from now. And they're quite simple, so I'm not going to go through those in any detail. But let's take a look at binary tree delete somewhat carefully to see how it's working. It's somewhat similar to the character list delete function that we looked at in the previous lecture, but because the binary search tree has left and right subtrees, there is a subtlety that we have to worry about. So here on slide 11 is the code for this binary tree delete function. Let's remind ourselves that in main we called binary tree delete with the address of the header node, that is the address of the top variable in main. So if we draw a diagram now of binary tree delete having been called, once again we're going to have ptop pointing at main's top variable. Now the first thing we have to check is there anything in the tree? If star ptop, okay, here's ptop, here's star ptop. If star ptop is 0, that is if top is 0 so that there's nothing in the tree, then there's nothing for the binary tree delete function to do and it's all over. But in our case, star ptop is not equal to 0, so star ptop is equivalent to true. And what does that imply? Well, here we have the node at the top of the tree. When we were dealing with linked lists, we had a simple situation where we could delete the node at the front of the list after we made the header node point past it to the next element. But in our case, the node has two subtrees. It has a left subtree and a right subtree. So we have to be a little more sophisticated here. What we need to do, if the top of the tree has a node in it, recursively we will need to delete the left-hand subtree first, and after it's been deleted we'll then need to delete the right-hand subtree next. After both the left and the right-hand subtrees have been deleted, we'll be able to delete the topmost node from the tree and then set our header node equal to 0. All right, so let's step through this statement by statement. So ptop is pointing at top. Star ptop, that is top, is not 0. So we are first going to execute binary tree delete, passing in the address of the left subtree of star ptop. Okay, here's ptop, star ptop is top, star ptop in parentheses arrow left is this pointer variable within that BT node structure. We're passing the address of that thing to a recursive call of binary tree delete. All right, so let's do that. And here we are. So we've called binary tree delete, and its ptop is pointing at the left side of the node containing the 12. All right, so now we start executing this inner binary tree delete function. If the tree is empty, we don't have anything to do, but in our case, star ptop is not 0. That means that the left subtree is not empty, so we have to invoke binary tree delete on the left subtree of the node containing the 7. That's going to create another recursive call. And in this third recursive call, ptop is now pointing at the left subtree of the node containing 7. Now the left subtree of the node containing 7 is 0. So when we get into the code for binary tree delete in this third recursive call, star ptop is 0. Therefore the delete function, the binary tree delete function, doesn't do anything, it simply returns. And so now we're back up a level at this point. So we've done our binary tree delete of the left side of the node containing 7. Now we need to do our binary tree delete of the right side of the node containing 7. But we can see that there's also a 0 on the right side, so that also is not going to do anything. So now we're at this statement, delete star p-top. Well, p-top is pointing at the left member of the node containing 12. Left, in turn, is pointing at the node containing 7. When I therefore say delete star p-top, that's going to deallocate that node containing 7. All right, so that node is now deallocated. And as a final step, we're going to assign to the left member of the node containing 12 a null pointer. All right, so that now indicates that the left subtree of 12 is empty. So the recursive binary tree delete call has now finished its work. It returns, and we're back in the original binary tree delete function. All right, well, that original binary tree delete function has just returned from deleting its left subtree. When it deletes its right subtree, there isn't actually anything to do because that subtree is empty. So we come down to deleting star p-top. That's going to delete the node containing the 12. And as a final step, we're going to set star p-top. That is, we're going to set the top variable in main to 0. And binary tree delete, the topmost execution is now done. It returns. We're back in main. Top has been correctly set to 0 to indicate that that tree is now empty. If I pass top as an argument to put binary tree will correctly not display anything. And we're done. Okay. Okay, so here on slide 13 are these implementations of binary tree is empty, which returns true or false, and binary tree min, which returns the leftmost value within the tree. All right, so we have made binary trees somewhat convenient for application developers to use by defining a collection of interface functions for creating binary trees, inserting values into binary trees, deleting binary trees, displaying binary trees, finding out about the contents of binary trees, etc., etc. We can expand this collection of interface functions. But there are several things that fall short in our implementation. For one thing, there's no automatic initialization. We would like to be able to just declare a binary tree variable and have it exist as an empty binary tree. It's ugly to have to call a make empty binary tree function. Also, the syntax involving pointers and pointers to pointers is frankly too messy for relatively junior programmers to deal with. The function names are long and clunky. It's also very easy for an inexperienced programmer to wreck the tree by just assigning nulls into the tree willy-nilly in various random places. We don't have any convenient assignment for assigning one binary search tree to another. We can't compare two binary search trees for equality using the double equal symbol. And users can write code assuming that the implementation of the binary search tree is never going to change. For example, if the user knows that the make empty binary tree function just returns null pointer, the user may decide, well, I'm just going to set the thing to null pointer and not bother calling the function. That will break if I later release an updated version of the binary search tree in which the make empty binary tree function does something more sophisticated. All right, so all of these problems we are going to fix by turning our binary search tree collection of interface functions into a binary search tree class. Then, by adding templates, which we'll get to later, very briefly, frankly, we'll see how we can take our code and have it work for a binary tree of characters, a binary tree of doubles, a binary tree of employees, perhaps sorted by name, and any other kind of binary tree of copyable objects. Okie doke, so that is that.